Welcome. Today's notes worksheet is entitled A Variety of Equations. We'll just look at solving a couple different types of equations today. And actually a couple interesting concepts come up when doing this, so we'll kind of see that in action as we go through this notes worksheet. But it looks like I do have an investigation to start us out here, and you do need a graphing calculator for this, so if you can grab one that would be great. And I'll kind of walk us through and see what occurs, and then we'll go through the process of solving some of these algebraically. So here we go. The investigation at the top says solve the equation x minus 5 equals the square root of x plus 7. And obviously we haven't seen an equation of this form before in the square root family, so I obviously gave you the hint as to how to go about doing this, and I'll do the work fairly fast here. We'll go ahead and get some practice with this later on, and I'll definitely slow it down for you. But for right now, I want to get the concept out. And in this case, as you can see, I do want to square both sides to get rid of that square root. And the reason for doing that is square root and square would cancel, and I get just the quantity underneath there, which was x plus 7. Now the left-hand side, I do have to be probably a little more careful with. This is square of a binomial. As we all know, it's not just x squared and 5 squared. I would do x squared minus 10x and plus the 25. So just be careful on that piece. And here's what's kind of interesting initially. By eliminating that square root symbol, I've actually changed the type of equation it is. Now it's a quadratic. Do you see that? It's now just a quadratic where I have the x squared over here, and I'm probably going to want to set this to 0. So I'm going to go ahead and just put this in our nice default position, that standard form. So x squared, let's bring the x on over, minus 11x. Let's bring the 7 on over, and I get 18, and that equals 0. That's pretty cool, actually. Because as a matter of fact, once it is set to 0, kind of run through those methods that we looked at when solving quadratics, and obviously, again, we've got that foundation under our belt. X and x, I'm thinking minus 9 minus 2, and wow, here we go. X equals 9, x equals 2, and that looks pretty good. But if you kind of notice, there's a question posed right away, and there's more stuff to this. So let's go ahead and look at it. It says, how many solutions do we apparently get? Well, based on my math, and I think I did all my math right here, by the way, it looks like we get 2 solutions, the 9 and the 2. Well, let's check them in action here. I'm going to do this graphically initially, and then we'll go back and actually look at the equation too. But let's see, we're going to graph the left side of the equation, graph the right side of the equation, and find out the points of intersection there. And those points of intersection would be the solutions to the original equation. If I do this and find out where they're the same, those should be my solutions, right? Well, let's bring up that calculator. So here we go. And guys, go to the y equals for me, and let's just type in x, here's the minus, and 5. Cool. Now it says go down to the next one and type in square root, so second, and then that button right there, square root, and then x plus 7. And that's looking great. I'm going to get a window that should work nicely for this one. So everyone hit the zoom button at the top for me. And let's go to the standard window. We'll be using the standard window a lot. And there would be the 2 sides graphed on the coordinate plane, and the point of intersection, or points of intersection, would be the solutions. And what do you notice? Which x value? Well, first of all, how many points of intersection are there? I just get 1. And by the way, what is the x value there where they intersect? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. When x is 9, they intersect. And so what do you see, guys? In this case, how many points of intersection are there? Just the 1. So the 9 works. What happened to the 2? Well, let me bring it up one more time. If you notice, when x is 2, well, the one side of the equation produces this, the other side of the equation produces that. Obviously, hey guys, they're not the same, and it didn't work. But I thought I did all my math right. So let me kind of read what I have on our sheet here, and then we'll go back and even look at it in there. And here's what happened essentially. When we solved the equation algebraically, we changed the form and hence the conditions of the equation. We had, originally, we had a square root equation, right? And square roots have particular conditions to them in the real number system. Specifically, we can't take the square root of a negative. So they have very specific conditions that they work under. When we changed it to a quadratic equation really doesn't have any conditions to it. It's a totally different type of equation. So something that may work here, unfortunately, might not work back here. And so as a result, trying to make a long story short here, as a result, we created what is called an extraneous solution. So an extraneous solution, as it says, is a solution that works in the modified equation, the quadratic, but not in the original. And as a result, guys, it's not part of our solution set. So you know when teachers tell you to check answers to make sure if you got it right? Here you actually have to. Watch what happens. Let's go back to the original. I'll put the 9 in. And if I do 9 minus 5, it's 4. 9 plus 7 is 16. This is the principal root, only the positive root. There is no plus or minus here by any means. This is just the principal root, a single number, and the principal root of 16 is 4. It worked. And that's what we saw graphically, by the way. When I try to put the 2 in, look what happens. I'll do the right side first. 2 plus 7 is 9. The principal root of 9, if I was to have you to plot this number on the coordinate plane, or actually, I'm sorry, on just a number line, on a number line, you would just plot it right at positive 3. Square root of 9 is 3. But if you look at the other side, everybody, 2 minus 5 is not 3, it's negative 3. It doesn't work. So what worked in the quadratic does not work necessarily in the original. We have to check. So what we would do, that goes, that gets boxed, and that's our solution set right here, just 9. So we do have to be a little careful. When you change the conditions, you might get an unintended consequence, so to speak. A solution that worked in the modified, but does not work in the original. So we've got to check. All right, so let's do a few of the radicals here and just make sure everything is legitimate. I gave you just a quick strategy, and then we'll just try a couple here. Isolate the radical and then raise it to the appropriate power. That makes sense. So obviously, guys, if I'm going to solve for the variable in this case, that variable right now is really stuck underneath a cube root. I'm going to have to deal with that cube root. So first order of business is, you know, to deal with a cube root, you're going to have to cube it. Would I dare to want to cube it at this stage? Would I want to go ahead and put a cube here and a cube here? Probably not, because if I cube the left-hand side, it's not just this cubed and this cubed. It's a binomial cubed, which is just a disaster, especially with this thing right here. So notice what it said. Isolate the radical. So long story short, bring the 4 on over. Now we can go ahead and undo the cube root by cubing both sides. And again, you've kind of looked at equations in previous courses before, and it's always just you keep unwrapping the operations in order to get the variable by itself. Well, again, what I would probably do is undo the minus 4 first. Then I would undo the cube root. And so that's what I'm doing. I undo the minus 4 by adding 4. Now I undo the cube root by cubing. And so I do get 3x minus 5. 4 cubed is 64. I'm just going to bring this on up here. And again, just undo the operations. Add the 5, divide by 3, and I think we're in good shape. So I add the 5, I get 69, and divide by 3, and I think that's going to work. Now you'll start to kind of see when they will potentially get extraneous solutions and when not. In this case, it does work. If you put 23 back in, it works perfectly, just so you know. All right, well, let's spend our time, moving forward onto the next piece. This one is going to mirror what the investigation one produced. So let's take a look at this. Square root of 12 minus 2x equals x minus 2. What value or values would make this equation true? So first order of business is really in order to get a variable by itself, I do think that square root symbol has to go away. And so I'm going to get rid of that square root symbol by squaring. But of course, whatever I do to one side, I must balance and do on the other. And so I have that piece right there. Okay, now again, good news is square root and square would cancel. And so I'm just left with that quantity 12 minus x. Bad news is I have to do it on the other side, and I have to go ahead and FOIL that out. If you were to do x minus 2 times x minus 2, which I'm hoping you're all able to pull off pretty easily, you should get something along these lines right here. And you can see, basically, when I did that, I end up creating an interesting quadratic equation. And so I'm going to go ahead and solve that quadratic equation. Let's go ahead and set this to 0, everybody, and see what plays out. I'm going to add the 2x. Negative 4x plus the 2x. Oops, should be minus 2x there. Let's get rid of that. There we go. And let's go ahead and bring over the 12 as well there. And 4 minus the 12 should be that. All right, looking good. Try to factor it, of course. I'm going to do that right up here. X and x, minus 4 plus 2, looking great. Now I'm rolling because I know x is 4 and x is negative 2. And I know for a fact these answers both would make that quadratic equation true. But, everybody, it's not whether it makes this true, it's whether it makes the original true. And so I have to check, guys. You have to make sure it works in the original because I changed the conditions of the problem. So 12 minus 2 times 4, is that equal to 4 minus 2? Let's go ahead and do a quick peek on that. And again, here we go, 12 minus 8. 12 minus 8 is 4. Take the principal square root of 4. Square root of 4 is definitely 2. 4 minus 2 is 2. It works. Good. That's part of my solution set right there. Let's check that negative 2 out just to see what happens. So I have 12 minus 2 times negative 2. And then what do we have on the other side? Negative 2 minus 2. Again, 12 minus 2 times negative 2 looks to be 16. And again, square root of 16, it is just a single number here. I'm not undoing a square or anything like that. I'm getting one particular value, and this is considered the positive root of 16 or the principal root of 16, and that would be 4. And then I go over here, negative 2 minus 2 is negative 4, and that doesn't work. So there's your solution, and there's not. So just be careful. It just so happens that in each case, one worked and one didn't. We could find a situation where both work, so please check both. You could find a situation where neither one works. So just be careful. Please check those answers. Has to work in the original. All right, now it gets hard. Yikes. Example 3, 2 roots. And how are we going to pull this one off? All right, well, let's see. I'm going to follow my instructions to myself, essentially, and to you. I'm going to isolate a radical. Unfortunately, I have 2 radicals. So one thing I'm looking at, just as we go through the process here, you want to square, right? The question is, would you square at this stage? Is it that simple where square root and square would cancel with the plus right there? And as much as I would love for it to happen, this does not work. I can't just go ahead and get rid of those by squaring both sides. So unfortunately, that is not our play. We've got to find another approach. Because I'm hoping you would all agree that this would be a binomial that you would have to square, and it's not pretty, not at all. Not that this one's going to be pretty by any means as it is, but let's at least make it a touch better. So what I mean by that, everybody, is isolate a radical. And because we have 2, I've got to just make a decision. So I'm going to bring this on over to the other side and isolate this one. Now again, do I want to do this? Let me rephrase. Do I want it to be simple? Yes. And will it be simple? No. So we're going to have to kind of muddle our way through it, but we don't have an option if we're going to solve it. So let's go for it. Here we go. I square, That should get rid of this root right here, and I get 3x plus 7. Now again, just good algebra, everybody. That's what it's all about here. I'm going to square the right-hand side too. And obviously we've seen it before. This does not just square square. We do have to FOIL. And I would ask you to FOIL. So here's what you're going to do. You are going to pause the video for just a moment. And I need you to FOIL this out. So officially, just FYI here, you don't have to write this. This is 1 minus x minus 2 times 1 minus x minus 2, as we of course know. So what would that look like? What would the right-hand side be? And then let's go for it. Well, when I did this, I FOILed, I got the 1. It looks like I got 2 of the x minus 2's. So let's see that. Oh, I'm sorry, and actually it's x plus 2. So good fix. My apologies on that. So let's fix it all the way through there. Good, finally caught that piece. So I've got 2 of those, right? X plus 2, and then plus x plus 2. Yeah, there we go. That's looking good. So when I multiply these two together, the square root goes away, essentially. All right, good. Let's go get them. Not pretty, right? It's time to isolate again. So here's the dilemma on this one. I isolated once, got rid of that. Now I'm going to have to isolate again and do it one more time. That's the issue on this one. Okay, so I'm going to do this in a couple different steps. I'm going to bring over the 1, everybody. I'm also going to bring over the 2. And I'm going to bring over the x. So I'm hoping you can see all of these things in action. If you can't, call me over and we can go through it slower. But I bring over the x, and I have 2x. I bring over the 1, that would give me 6. Bring over the 2, that would bring me down to 4. All right, very, very good. Okay, now let's see. We could actually, just FYI, because this is multiplication, you could square both sides, and this would be product raised to a power. I'm just going to practice what I've been preaching. I said isolate the radical, so I'm going to isolate the radical here. And so I'm going to divide by -2, and I get -1x minus 2. These would cancel, and I get root x, hey, plus 2. Good thinking, Mr. Meyer. All right, so good deal. Now, guys, we've isolated it. It's time to square. Here we go, one more time. Nothing like doing it twice in a problem. First time was really super unpleasant because of this square root right here. This one's a little easier. Let's see. Square root and square are going to cancel. I get x plus 2. Now, guys, FOIL that out for me. If you can, it works out really well. In fact, again, I see good things. There are ways to kind of work around this, even if this doesn't work for you. But ultimately, if I was to FOIL it, I'm getting an x squared, getting a 4x, and getting a 4. Wow, that is very, very cool because now I'm in a pretty good, comfortable position. The roots are gone, thank goodness. It took 2 times, but we did it. Now let's bring this on over and let's solve this quadratic. I get x squared. Looking at a plus 3x and looking at the plus 2. So this stuff comes over. Now I factor and solve. And x plus 2, x plus 1 looks great. And at this stage, it's looking like x equals -2 and x equals -1. All righty. Hey, this is, I'm not going to do the whole thing through. I've got my answer on my paper. I'll ask you. A quick pause, if you would, and check. See if you can pull it off. Put that -2 back in for x. See if it works. Put the -1 back in for x. See if it works. All right, when I did this, I got one working and one not. Which one is it? Say goodbye to that one, and I like that one. That one worked. So in this case, it looks like we did create this extraneous solution right here, so it's got to go. It doesn't work in the original. I think the -2 works out nicely if I remember. All right. Good. So, radicals, huh? Kind of cool. Let's try a different type. Factorable. All right, so now some pretty heavy-duty equations. We worked a lot with quadratics in factoring. Now what we're going to do, of course, is build up on some more of the other polynomials. So it says break the expression down into the product of factors and use the zero product property. Okay. Now, I've kind of given you the approach here. I would ask you if you think you can shortcut this. So look at that equation, and I am curious if you're thinking about shortcutting it. Please don't just yet. So when we were working with polynomials, we've done this with quadratics. We do it with these as well. We do want to set it to our default position. So no matter what type of polynomial equation I give you, I think what you want to do is set it to 0 first. Then we can break it on down, and we can apply the zero product property. So what I'm thinking here, everyone, is x cubed is definitely a greatest common factor there. That would give me x squared minus 4. That's looking good. I'm going to bring this on up, and I see x squared minus 4, and that breaks down even further to x plus 2, x minus 2. Good factoring techniques in action. And as we all know, we're supposed to set our factors to 0. You know, officially I have 3 factors of x set to 0. I'll just do it like that for the time being. And then I get something like that right there. You know, here I guess I would cube root both sides. Cube root of 0 is 0. Subtract the 2, get negative 2. Subtract the or add the 2, and I get 2. Now, here guys, I will tell you, all 3 work. We didn't change anything here. We just set it to 0 and we solved. So don't worry about extraneous solutions on these polynomials, really only on the radical equations. And that's it. And by the way, if you put 0 back in, it works. If you put negative 2 back in, it works. And if you put in 2, it works. All right. Now, notice what I put on your paper here. I guess I called it just a little red flag. Something to be wary of. I've seen students over the years try to shortchange this a little bit. Rather than setting it to 0, seeing an equation like this, and try to shortcut it. And what would be what I guess you would consider the shortcut? Well, I've seen students over the years, they would immediately say, hey, wait a minute. I can just divide both sides by x cubed, because dividing by one side and the other should, you know, still keeps it in equilibrium. These would cancel. I get I get the 4. Here I get x squared, and I would get undo the square maybe, and I'd get plus or minus 2, and be like, oh, wait a minute, those do work, and those are our answers. But what happened, of course? Was this the most complete solution set when I divided by that variable factor? And unfortunately, no. When we divided by this variable factor right here, we lost the solution that came from it, and we never got that 0. So even though it is like algebraically legitimate, it's not. So we can't divide by a variable factor. That's the thing. Working with equations, it's great that you want to keep that property of equilibrium intact, but you do have to be careful. Dividing by a constant does not preclude us from getting all the solutions. But when you divide by a variable, it does potentially preclude us from getting it. All right, so long story short, red flag. In an equation, don't divide both sides by a variable factor. And that's not probably the best way to phrase it, but I think it suffices here. So don't divide it by a variable factor because you lose the solution. Potentially. Most likely. In this case, we did. So again, guys, with these, set it to 0. That's the bottom line. It looks good. It looks tempting, doesn't it? Just like even on that other one where we wanted to kind of just square quickly and be done with it. Yeah, unfortunately here, we can't just divide by x cubed. I mean, what we did is right. We just didn't get the whole thing. Cool. Well, let's go get just a little experience with these, and then I've got one pretty cool thing to show you. All right, wow, interesting. Let's see if we can solve them. All factorable. I've got a cubic, quartic, and a degree 6. Oh, awesome. Here we go. Let's start them out. So, factor. Look at the 4, 24. I'm going to pull out a 4. X cubed, x squared, and x. I'm going to pull out an x. And when I do that, it looks like I have an x squared minus the x. And how about minus 6 would do equals 0. Everyone okay with that? And what you're trying to do is break this down into a product of factors. Talk a lot about factoring at this level of algebra. And so let's continue that discussion. There we go right there. And I'm thinking x minus 3, and how about x plus 2? I hope that looks good to everybody, as a matter of fact. So what I did is took this in standard form, broke it down into a product of its factors. And now the 4 is sort of irrelevant, but I'll keep it for the time being. I mean, basically it doesn't hurt. But now I just take all those factors and I set them to 0. Divide by 4, get 0. Add the 3, get 3. Subtract the 2, get negative 2. And for that cubic, you see 3 nice real numbers there. Beautiful. So pulled out the greatest common factor, saw a quadratic left over, broke it down, 0 product property, no issues. All right, let's up the ante here, everyone. Degree 4. Now this is an intriguing one because, quite frankly, I don't think I can break it down using a greatest common factor here. There's nothing that I see goes into those right there. But I'm wondering if its form just kind of, if it looks familiar. Even though we haven't done really degree 4 polynomials, it has a certain look to it, doesn't it? I've got an x to the 4th and an x squared and a constant here. Doesn't it have that feel of being quadratic? And if it has that feel of being kind of a quadratic trinomial, why don't we see if we can break it down into 2 binomials side by side? I think the major difference here is instead of x and x going in the first, it would be x squared and x squared. Because multiply to x to the 4th, and now, guys, would those combine to an x squared in the middle? Sure. So again, it has that same exact ring to it as those quadratics. Now I could just kind of play it out first outside, inside, last. 2 numbers that multiply to 20 and combine to negative 9. I'm seeing a minus 5 and a minus 4. So at this stage, everyone, does this seem like this is the factored version of this right up here? Yeah, sure. Now, by the way, I do know x squared minus 4 breaks down further. You can do x plus 2, x minus 2. I don't know. I mean, you can do that if you want. I think we can get away with it without doing that. And I'm going to try that here, if that's all right with you. 2 factors set to 0. I do have to be a touch careful with this. As we've seen, quadratics have 2 solutions to them. So when I go ahead and do that piece right here, and now I undo a square, notice the major difference here. I'm working in an equation where I am undoing a particular square. And when I undo the square, I do take both of the roots of 5. And when I undo a square over here, I do take both of the roots of 4. And there we go. Great way to just see if you got it right. Put them in. Put root 5 back in, it works. And when you put negative root 5 back in, raising it to the 4th and raising it to the 2nd, it's the same as doing it with the positive root 5. So all 4 answers work. Pretty cool. So keep that in mind as you kind of go through those great factoring techniques. They really, they work well in a variety of types of equations. Let's see if we can go get this degree 6. Wow. Okay. Well, the only thing I know to do in terms of traditional factoring methods is, with 4 terms, is to try to group it. So let's give that a try. And group here, group here. All right, here we go. So I'm going to do x to the 4th, pull that out, and I get x squared minus 4. Okay, this is good. I'm going to pull out a minus 1, because if I pull out a minus 1 Oh, there it is. Then I get x squared minus 4. That's looking great. So it is a candidate for grouping. So let's play it to its conclusion here. Two terms, this one and this one. Each term has x squared minus 4 in it, so that's coming out. And then I get x to the 4th minus 1 equals 0. All right. Now here's the thing, and we'll talk more about this over the course of the year. I'm actually going to get 2 solutions from this one, so let's make sure we do get that. And I actually should get 4 solutions from this one, so let's see if we can get that. Now I shortchanged the x squared minus 4 over here and went this route, and it worked. It was perfectly fine. I got 2 and negative 2. I am going to go all the way through here because I want to go all the way through on this one. This factors quite a bit more. You ready for it? Okay, this is a difference of 2 squares. X plus 2, x minus 2. And of course, guys, that's going to produce the plus or minus 2. No doubt about it. This, guys, again, recognize that's a difference of 2 squares. X squared plus 1, x squared minus 1. Okay. Now, again, I could probably get away with it here, but I'm going to go further on what I can. X plus 2, x minus 2. There is no sum of 2 squares. That's prime in the real number system. This one, though, is another difference of 2 squares, isn't it? And so look at that. A product of 4 linears, 1, 2, 3, and 4, and a quadratic. That's what makes up that degree 6. Very, very cool. Could we get all of our solutions from here, guys? I'm seeing 4 real numbers from here. And then could you set that to 0? Subtract the 1 and undo the square and get a couple imaginary units on that? Yeah. So I'm getting x equals plus or minus 2 from here and here. X equals plus or minus 1 from there and there. And then 2 pure imaginaries plus or minus I from here. Okay, if you just run into any issues on that, let me know, but that should be the case. Fascinating. If you put any one of those 6 back in, they work. All right, so good factoring, and now utilizing that in the context of solving equations. Perfect. All right, one last piece. If you've seen this before, that's fine. This isn't unique by any means. But basically, it's a good spot to put this because we've done a lot of things where changing something has sort of an unintended consequence. Like with the radicals, creating an extraneous solution, and with some of the factorable ones, maybe dividing by a variable factor has an unintended consequence. We lose the solution. So I thought it was a good spot to kind of put this little piece in right here. What I'm going to do, guys, is develop a mathematical proof, and I'm going to make the number 2 equal the number 1. And obviously, guys, 2 does not equal 1. So what I'd ask you is what's wrong with the proof? I'm going to try to be a salesman on this. I'm going to try to sell each and every step perfectly. But one of the steps I do is going to be wrong. See if you can figure it out, and then tell me about it. See if you can get it. So you ready for this? Just watch. You can write it down if you'd like. You can wow your friends and neighbors and family and so forth, or not. Here we go. Ready? Cool mathematical proof. I'm going to let A equal B. So 2 terms, property of equality on it. And now what I'm going to do is start manipulating each side of the equation by doing the same thing to it. That's the key. It's keeping everything in equilibrium. The first thing I'm going to do, everybody, is multiply both sides by A. Again, perfectly okay, because what I do to one side, I do to the other. All right, not bad. Multiply by A, I have that. Next step, everyone. I'm going to go ahead and do the same thing to both sides. This is somewhat arbitrary, but this is part of where I want it to go. I'm going to subtract B squared from both sides. Again, as long as I'm doing the same thing to both sides of the equation, we're still okay. So here multiplied by A, here subtracted B squared. Okay. Now, guys, recognize this factors. This factors. So here we go. That's a difference of 2 squares. And it factors beautifully. A plus b, a minus b. This one also factors nicely. Greatest common factor. Pull out the b, and I get a minus b. Awesome. I'm going to continue that progression that I did on the previous steps and do the same thing to one side that I do to the other. In this case, I'm going to divide by a minus b. Okay. Dividing by one side, dividing by the other, perfectly legitimate. As long as I keep everything in equilibrium, it's perfectly okay. Okay. Now, when I divide by that a minus b, I end up getting a plus b equals b. Okay, nice. Looking good. Now, actually, I'm going to go back just a moment here, and I like this equation. I'm going to do just a touch of substitution, if you don't mind. And remember how I started, you know, a nice, good arbitrary statement, but a good one. A and b are the same. And so what I'm going to do is, you know what, I'm going to take this b, and I'm going to put it right in for a. Substitution as they are the same. Okay, and I get that. And guys, of course, b plus b is 2b. Do that right there. Look at this, guys. And then same thing. What I do to one side, I do to the other. Just like I did here, as a matter of fact. Remember, I divided this. Perfect. I'm going to do the same thing here now. So dividing, same thing on one side as I do on the other. And look at that. How cool is that? So 2 is equal to 1. Now, everything I did, I said was legitimate. And so I did talk my way through, mathematical step all the way down, and I made the number 2 equal to number 1. So guys, obviously, where did I go wrong? So see if you can figure it out there in that proof. Not just which step, but why it's wrong. And actually, there's only one step. And that's what makes it go crazy. Alrighty, guys, I'll let you mull that over. Sorry to blow your mind there at the end of the lesson, but some pretty cool stuff with that. Just let me know if you have questions along the way with this. Get some practice. There's some good equations to solve on this piece. Thanks.